Well, hello, and welcome to this, the latest in our series of monthly webinars from the IEA Clean Coal Centre in the UK. My name is Colin Henderson, and I'll be presenting today on increasing the flexibility of coal-fired power plants, which is the topic of my latest report. The report itself will be available later this summer to download from the Clean Coal Centre website at iea-coal.org. Residents of member countries and employees of our sponsoring organisations can download these reports at no charge after a one-off registration. The slides that you will see today will be made available for download from our website later today. Before I start, a reminder that if you have any questions, you'll see that you can submit these as text using the box near the top of your screen. I'll do my best to answer these after the main presentation. And if you wish, you can include your email address in case we need to communicate further. I suppose we all like to see power generation having as little environmental impact as possible, and renewable energy sources certainly have an attraction in that respect, but they do have drawbacks. One of these is that the generation from many of them fluctuates. In the absence of practical means for power storage at the level required, this means that conventional plants are going to be needed for some time on power grids so that they can fill in the resultant varying gaps between supply and demand. To do this, they need to operate flexibly. The problem is that many were designed to operate at a fairly constant output. Today I'll describe some of the methods that can be used to obtain that flexibility. Most coal-fired plants use pulverised coal combustion, but there are other plant types as well, and later slides will cover some of these other systems. First, I expand a little on the growing need for flexible fossil plants. In Germany, for example, this slide shows the significant changes that are occurring there. The situation in 2010 is compared with that expected in 2020. By 2020, coal plants will have to fill a highly fluctuating gap between supply and demand to keep everything in balance at all times. At times they will need to be off, at other times they will need to be at varying output. There will also be more need to provide system frequency support, because increasing the proportion of renewables tends to reduce the inertia of power grids. There's a surprising variation in reported ramp rates for existing plants, perhaps because of a desire to limit plant wear. Values appear to be around 2 to 5% per minute on older plants particularly. They are generally more for some newer designs, and short-term response for frequency control can be 10% per minute or faster. So there's a growing need for very fast response in fossil-fired units. In the remainder of these slides, I'll look at different parts of the plants and how they can be adapted to achieve this. I'll start with the coal grinding and firing systems, which are in the area indicated here, not very subtly, but I didn't want you to miss it. While we're on this diagram, perhaps it will be helpful to refresh you on the main areas of typical pulverised coal-fired plant, which make up the vast majority of coal-fueled capacity. The boiler in this simplified diagram of mine here is coloured in yellow, and it supplies steam to the turbine here in blue. Air supply arrangements are in the lower left, and flue gas treatment systems in grey in the lower right quarter of the figure. Condensate from the condenser, which is green below the turbine, is pumped back into the boiler for re-evaporation into steam. The flexibility of a large power plant depends on all important links in the chain being able to handle large and rapid variations in output. So starting, as I say, with firing systems, including coal grinding and feeding, as well as combustion itself, what is the issue here? It has to do with particularly being able to get down to very low firing rates while keeping a stable flame without support fuel. Being able to fire at particularly low fuel feed rates allows the operator to keep the system on. There are few more costly operations than a shutdown and start-up, and keeping the boiler alight at very low steam production levels will reduce the need for this. This has traditionally been difficult, but as the next slide shows, it can be done. Mill and burner redesigns are allowing the previous 40% minimum to be improved upon a lot. So it is possible through changes to mill sizes with new burners to achieve 25% load on 2 mills, as shown in the diagram, bottom left. In some tangential corner-fired systems, the minimum load has been further reduced by operating a single mill to give turn down to less than 20% or even only 15%, as shown, for example, at Heilbronn Unit 7, which is shown in the photograph. It's even possible to go further. By modifying the pulverised coal feeding arrangements to incorporate hoppers for temporary storage of the milled coal, even lower burning rates become possible. The next slide shows that such indirect firing can achieve 10% load or even better. Decoupling fuel grinding from combustion means that firing rate is no longer fixed by the mill output at the time. A consequent reduction in the inertia of the system allows firing ramping rates of up to 10% per minute. The arrangement can also enable more power to be sent to coal grinding at times of lower electricity demand, and it is possible for the mills to operate more efficiently, improving net generation efficiency at low load. Interestingly, this indirect firing system is something which was first used when pulverised coal plants were introduced. It was only when mills became more reliable that it was phased out. Now it's having a rebirth. For lignite plants, which may typically at full output have 6 or 7 beta mills operating out of 8, systems are usually designed for a minimum load of 40% on new units, though only down to around 50% on older plants. 4 mills are usually in operation at the 40% load, but recent tests show that it is possible to operate on only 3 mills and thereby to achieve a modest further reduction in minimum output by a fine control of the air supply and mill speed adjustments. Tests at Vattenfall's lignite-fired Schwarzer Pumper plant achieved 37% of rating, and reaching down to 35% is considered attainable. Modern control systems can reduce the minimum load on legacy units substantially, as shown by RWE, and I've got a slide later illustrating that. Lignite pre-drying, which is actually aimed mainly for higher efficiency in future plants, would also provide a method for indirect firing with attendant ramp rate and minimum load improvements. In boilers designed for such a dried fuel, the tangential firing arrangement would use corner mounting of the burners for better stability. In fact, wall mounting with tangential firing is what is conventionally used in modern lignite boilers. As I say, change the corner firing would give a better stability. A minimum load of around 30% then would be quite likely to be obtainable. The next area of plant that I will look at embraces the pressure parts of the boiler, including tubes, headers and membrane walls. Conventionally, when base load operation was the norm, creep was the main deterioration mechanism to take account of in designing these large stressed components. But when plant cycling is more important, life consumption mechanisms become determined more by fatigue and fatigue interactions with creep and corrosion. Thermal expansion can also cause damage, not only to the main component, but also to the large ties that hold the pieces in position. So the main issues here are potential damage from stress variations. The key to solving this is to reduce the thermal gradients that will develop when load changes, so that the changes in stresses on the component are less severe. Ways in which this can be achieved are using new, stronger steels to allow reduced metal thicknesses, accompanied by using a different approach to determining the necessary component wall thicknesses that gives more weight to creep fatigue as opposed to creep alone. Other ways include increasing the number of headers or installing external steam heating or hot storage systems. So these would allow the components to be kept closer to operating conditions during short-term shutdowns, for example. Lower minimum load can be enabled by incorporating design features such as internally rifled tubing to enable reduced fluid flow rates without metal overheating, or by adding economizer or feed water heater bypasses. For the turbine, again, major issues that present themselves can be potential damage from stress variations. The very high temperature and pressure conditions of ultrasupercritical turbines necessitate use of thick wall components so that they possess adequate strength. Unfortunately, as in boiler components, this can limit the rate of temperature change consistent with keeping thermal fatigue to acceptable levels. One of the difficulties is the challenge of maintaining very small clearances between stationary and moving components that can threaten robbing or excessive losses during variations in output. As well as preserving turbine integrity, the other part of the story concerns actually achieving very rapid changes in output. The measures on this slide are all about, I suppose, basically being nice to the turbine to reduce the stresses. An example of a mean to control the rate of temperature swing in a thick wall component is steam cooling of the outer casing to keep its temperature slightly lower than that of the inner casing at the corresponding position along the turbine as the load is changing. This allows the thickness of the outer casing to be reduced in the design. Although throttling has been used traditionally to vary output from a turbine while keeping the pressure constant, sliding pressure operation has become a commonly applied method in supercritical systems. It makes matching steam and metal temperatures easier and maintains higher temperatures during shutdown, so this is all helpful with flexibility. Turbine bypass systems are a virtual necessity in plants designed for on-off and other flexible forms of operation. They allow all or part of the steam to bypass the high pressure or low pressure turbine so that the rate of temperature change in the turbine can be managed as the boiler is starting up and shutting down. Ensuring correct clearances are maintained during start-up and variable loads is important for maintaining efficiency as well as reducing wear. This requires careful design incorporating more forgiving sealing arrangements and measures for ensuring uniform thermal loading. So, for example, sprung segmented sections to labyrinth seals so that they can adapt in size to keep a suitable gap. As well as preserving turbine integrity and efficiency, the other part of the story concerns actually achieving very rapid changes in output, such as for frequency control duties. Methods available for primary frequency control include the well-established method of opening of throttled main steam valves, but also nowadays condensate throttling, feed water heater bypass, and HP stage bypass. Another alternative is to install a thermal storage system, which can also increase the load range. In condensate throttling, the turbine control system opens the governor valves to utilize the reserve steam storage capacity of the boiler, as in conventional throttling. But the flow of condensate to the low-pressure feed water heaters is reduced at the same time. The flows of extraction steam are thus reduced, leaving additional steam flow in the turbine, generating the additional power. Maximum output can be reached after about 30 seconds. Provision of feed water heater bypasses is another means to increase flexibility. It can actually help with reducing minimum load by allowing a reduced final feed water temperature, but it may also, in contrast, be designed to give a power boost. Use of high-pressure feed water heater bypass can produce additional power for up to half an hour by allowing more steam through the turbine. Even more flexibility can be achieved by installing storage systems for the low-pressure or high-pressure feed water. A simple example is shown here using a storage tank incorporating hot and cold water with displacement of each by the other during increased or decreased power requirements. HP stage bypass permits additional high-pressure steam to be admitted to the high-pressure turbine some stages after the first blade row when the bypass valve is opened. The system is normally designed to give a short-term 5% increase in power, but it can be designed for more. Normal operation at 100% maximum continuous rating is achieved with the stage bypass valve closed. Although efficiency falls upon using it, the HP stage bypass is the most efficient means available for achieving rapid load increases, about 1% per second, because throttling losses are a minimum, because full arc admission is possible throughout. And you can use this system over the whole load range, unlike for throttling, which tends to be where the boiler is kept close to maximum rating, ready to respond. A plant's emissions control systems also need to be able to cope with load swings, low loads and shutdowns while preserving their effectiveness. Particular control systems can usually cope with rapid load changes without problems as long as temperatures remain above the acid dew point. For SCR NOx reduction systems, which are usually placed after the economizer, the main potential issue is the possibility of lower than designed flue gas temperatures occurring during low load operation. SCR units often use ammonia as reagent, and ammonia control may become difficult during fast load swings, leading to formation of ammonium bisulfate, which forms as a sticky liquid, and this can fill the catalyst pores and deactivate it. It can also give a problem in the air heater with deposits. For flue gas desulfurization to operate well, precise control of the reagent and water flows and flue gas temperature is needed. Varying load can affect both performance and reliability. Shutdowns are particularly unwelcome as warm-up periods are very long. For SCR, selective catalytic reduction, to avoid problems with ammonium bisulfate formation, the conventional solution is to add a flue gas or water side economizer bypass to enable the flue gas temperature at low load to be kept at design value. Other options include closer monitoring of conditions, changing the coal, and modifying the inlet temperature distribution using baffles. Whatever method is used, provided the correct temperature can be maintained, rapid rates of load change can generally be accommodated with retention of performance. For FGD, it can be possible to obtain savings in energy consumption of part loads by using improved control systems and switching off some of the circulation pumps. The number of shutdowns and startups needs to be minimized also to avoid slurry solidification and accumulation of residues on the linings, quite apart from averting the long warm-up periods. Keeping within the required emissions limits during rapid load changes requires very careful control, and an increased liquid-gas ratio may be needed. Particular control systems can usually cope with a plant operating at partial load and rapid load changes without problems. Inlet gas temperatures need, however, to be watched. They must not fall so low that acidic moisture condenses on particles, because this can cause adherence of solids to bag filters, causing an increase in the pressure drop, or a resistivity problem for the ESP to perform efficiently. It's generally worthwhile replacing control and instrumentation systems in older plant to increase efficiency and flexibility. Sophisticated control and instrumentation will also improve minimum load capability, for example through additional flame monitoring. RWE has carried out control system retrofits on its 300 and 600 megawatt lignite-fired units to achieve greatly increased ramp rates and lower minimum loads, as shown in the figure. Again, with respect to control systems, boiler and steam systems responses are significantly different at low load from when close to full output. And this effect becomes greater when deterioration mechanisms come into play when a plant ages. This can affect the response of the boiler, and control performance can become degraded, and flexibility therefore suffers. Modern systems can actually stabilize such non-stable loops. Modern monitoring and control systems can also keep temperatures and clearances in the turbine under better control during start-up and load changes, so you have a more accurate picture of how the different parts are expanding as the load is changing. In a promising development area, self-learning predictive systems will coordinate all the plant's main systems, optimizing the whole plant. This should be highly beneficial in realizing greater flexibility through reducing stresses on plant components while maximizing the efficiency and maintaining minimum emissions. And while as shown here, modern control can enable combining the operation of multiple units, remote monitoring and coordination of large numbers of major units is a possibility for the future for maximizing overall availability and flexibility of supply onto grids. Not all coal-fired power plants use pulverized coal combustion. CFBC, circulating fluidized bed combustion, has a significant share of the market, while integrated gasification combined cycles are slowly deploying, and very high temperature pulverized coal, advanced USC or AUSC plants are in development. Coal-fired carbon capture and storage plants are also in prospect for the future. The next few slides consider the flexibility properties of these. For CFBC, the flexibility issues of the turbine and water steam cycle would be expected to be similar to those of pulverized coal plants. However, the boiler arrangement and fuel combustion arrangements can limit minimum load to about 40% of MCR in the absence of supplementary fuel. That having been said, reasonably good load following capability can be achievable, and in some instances a minimum load of 25% is possible. CFBC is less well suited to on-off cycling, as the bed temperature needs as far as possible to remain within normal operating range, and there can be potential for refractory damage. Coal-fueled IGCC power generation uses a combination of gas and steam turbines to produce electricity. It's a bit like a natural gas-fired combined cycle plant with a front-end coal gasifier, which is usually fed with oxygen. These systems have not hitherto been designed specifically for high flexibility, and the minimum load is conventionally about 40 to 50% of nominal output, limited by the minimum outputs of the gasifier and oxygen production unit. With more than one gas turbine, there is more scope. The ramp rate of a standard IGCC, though limited by the gasifier and oxygen production ramp rates to about 3 to 5% a minute, is comparable actually with that of many older pulverized coal units. Polygeneration systems, which are plants designed to give varying balances of multiple products, including electricity, liquids and synthetic natural gas, would have higher load ranges because you could switch between products, though not necessarily very quickly. Another way would be to incorporate storage of liquid oxygen or nitrogen. Another means may be addition of natural gas to the syngas to increase ramp rate and output as required. Certainly if IGCC plants become common, designing for flexibility will become more important, and further new approaches to achieving it may well emerge. Advanced ultrasupercritical plants are advanced PCC plants with steam temperatures and pressures of 700 degrees Celsius, 35 megapascals or higher. There are programs in different parts of the world to develop them, driven by the desire for higher efficiency, to lower emissions and to reduce fuel costs. They'll include advanced nickel-based alloys for the hottest parts of these plants. None have yet been built, so lab tests and studies are all that we have to go on in assessing their likely flexibility. Unfortunately, nickel-based alloys have the disadvantages of low thermal conductivity and high thermal expansion coefficient. These properties would potentially give rise to higher thermally induced stresses during changes of load than in current plants. Work on the design and development of the large superalloy components will have to overcome this if the AUSC plants are to achieve the flexibility needed for use in power markets such as in Europe. Estimates show startup times up to 50% longer than for current USC pulverized coal systems. predictions, and many are, that coal-fired plants incorporating CO2 capture and storage will be operating in significant numbers from about the mid-2020s, with major deployment during the 2030s. A proportion of these may provide baseload alongside nuclear plants. However, many will need to operate flexibly, as wind and solar energy plants will still be called to operate first. Again, there's no direct experience of large, by that I mean 100 megawatts plus CCS power plants operating, though plants are about to start later this year in Canada and the USA. But a number of ways in which these plants may be designed to achieve flexibility have been studied. There are three main technologies for CO2 capture: post-combustion capture, which is flue gas scrubbing on pulverized coal; oxy-coal combustion, firing pulverized coal with oxygen; and IGCC with pre-combustion scrubbing, so that hydrogen is fired in the turbine rather than a mixture with CO. There's not time or space to go into any of these in detail now, but the slide summarises some systems that are being considered for achieving the flexibility in these systems. The last idea, hydrogen storage, looks particularly interesting for IGCC with CO2 capture. The gas could power open cycle or combined cycle gas turbines, which could feed off the stored hydrogen in an underground cavern. I'm reaching the end now of this presentation, and this slide summarises the main points. High flexibility of coal-fired units is needed on power grids with large capacities of renewable energy generation. Synchronous capacity will be indispensable for some time in order to support the grids. The main requirements of flexible coal-fired units are capabilities for rapid startup, fast load following, and grid frequency stabilisation. Potential life-limiting effects of plants cycling are known, and new systems give high flexibility with good plant life and thermal efficiency. Of course, there are all sorts of ways of making adjustments and changes to existing plants and to increase their flexibility, but I've introduced just some of the main ones. It's not known for certain how much flexibility the advanced ultrasupercritical or IGCC plants could achieve ultimately, but it may be possible to exploit energy storage potential of the latter. For future CO2 capture plants, there are a number of possible ways of achieving flexibility that are being looked at. Well, that's enough of me. Thank you for staying on to the bitter end. If you do have any questions, I'll be pleased to attempt to answer them now. So I'll just have a look and see. I think I've got one at the moment. This reads, "Hello Colin. For SCR low load situation, an additional solution is to implement a hot water recirculation system to reduce the heat transfer in the economizer during start-up and low load." Right, yes, thank you very much for that. Yes, it's all a question of getting the flue gas temperature to the right level so as not to cause problems with the operation. Another question or comment? There are a number of plant elements that can be the limiting factor for load following. What is the most common sticking point for load following? On legacy plants, it's probably the high pressure components within the boiler, and also large metal components in the turbine side. So it's the legacy thickness with the old materials. But modern plants, it can be tackled by using new materials which can be thinner, and by careful design of the turbines. And it's possible to, admittedly with quite a lot of money, to completely retrofit turbines, have new systems, new casings and so on. So that's two questions. While I'm waiting in case there are any others. The slides will be available to download as a PDF from the webinar area of our website later on today, as I mentioned before. And if you missed any of it, you'll be able to listen to the commentary with them again via Bright Talk. Okay, well, the IEA Clean Coal Centre will be presenting another webinar in September. We don't know what it is yet, but there will be. More information will be available soon about this on the website. But anyway, thank you very much for listening, and thank you and goodbye.